webinar event, and we're excited to be able to have Kyle and I guess Baxter, and actually I missed their special person there, but they're representing, yes, that's right, from RFQ. I'm sorry about that. So we have them representing from Henkel Loctite, and they're going to present the first part of the two-part series on the use of medical adhesive in medical device development. So with that, I apologize for the technical difficulties and the delay that we've had. And without much further ado, I'll just hand this off to Kyle.
Okay, thank you. Hopefully everything will go smoothly from here because there was a lot of behind the scenes getting ready. I'm glad we came early. Are they supposed to get food now, too, Julia? If anybody wants to eat? Because you're eating, I'm presenting. That's the good part, right? Yep. So if you don't have a binder, you might want to pick one up in the back and just raise your hand, and Baxter will get it for you, I'm sure. The binder has a copy of my presentation notes in it under Section 3. So if you want to follow it that way and you want to write your own notes, this is your binder, as Julia mentioned at the very end of the presentation. We're going to do a second one in May. I can't tell you the date because I can't remember off the top of my head, but we'll give you a reminder. Oh, hi.
Hi.
I haven't seen you in years.
I'm everywhere.
Yeah. So anyway, old friends, feel free to ask questions. This is not as interactive as the second one because the first one we're focused on more the design of medical devices. So we'll focus on, well, I'll go through the agenda with you in a minute. The second portion will be more focused on the actual adhesive. Although, since we manufacture adhesives, we're happy to entertain any questions on adhesives and how they're used. Okay? So let's just take a look at the agenda. I don't remember how. Am I not? Did we just hit this? Okay, there we go. Okay, sorry, being a little help there. So first we're going to start with adhesive joint design, something you probably don't get when you go to engineering school, right? Oh, and let me just back up for a second. How many people here are involved in the design of medical devices or have some input in it? Everybody. Okay, perfect. So what we'll focus on there are the types of forces that can act upon our adhesives and the joint. I call it the good, the bad, and the ugly because some are far more challenging than others, and we just want to make you aware of those so that you can either impede that force as much as possible or design around it or away from it where possible. The next section we want to talk about is bonding plastics, and I'm going to show you a guide that Henkel created, I'm going to say 15 years ago, but time flies. We've updated it many times over the years, and it's going to be your go-to guide, I think, before the session is over, so that you can go to and really kind of figure out what are the substrate options that I have. Do I have an opportunity to bond and get the kind of adhesion I'm trying to get, or is there something I could do to the surface to make it more bondable? So that'll give you some good options. Then we'll talk about sterilization resistance. We know as medical device manufacturers you have to sterilize your parts, so we'll talk about the ones that are most commonly used. Try to give you a sense of how our adhesives withstand those sterilization methods. Biocompatibility testing, we actually started that program back in 1981 when we first introduced medical products, and we have continued to upgrade that program to where today it's an ISO program, inclusive of USP Class 6. So we're not regulated by the FDA, we're not required to do it, but because our adhesive cures into plastic, either a thermoplastic or a thermoset, we treat it as if it's a plastic. And so we send them out to do the toxicity testing, and you can pull down those certificates of compliance right off of our website, if you can navigate our website. That's the trick. And the last piece, which really doesn't fit, but because I know I'm going to be loaded with a lot to talk about in the next one, I plugged in the epoxy urethanes because it's a little bit shorter piece of the presentation, so we'll focus just a few minutes on kind of the benefits, the limitations of those chemistries, and why they're used and where they're used. And that's really the focus of it. Any questions on the agenda? Or is that kind of what you were hoping to learn about? Okay. Yes?
Stupid question.
Probably not.
The interrelations between Loctite and Henkel and the old Henkel, I used to know both products in separate companies and others.
Yep.
And now you have Nordson in there too.
No.
Okay, I'm sorry.
Yeah, that's another. Okay,
that's a different. Okay,
but
okay. Have you merged some of the products, or how is that?
It's complicated, but to give you a short answer, Henkel acquired Loctite in a hostile takeover. I'm going to say, I can't even tell beginning of the year that it was. We went along merrily about our way as Loctite, you know, and just kind of was minding our own business. And then we started to notice, wow, someone really has bought us. We saw the changes start to take place. So there has been some merging. We also acquired Hysol along the way.
Right.
So we've kept the brands, Loctite, Hysol, and some of the others. And while we say we're a global company, we can pull from some of those other areas, would be, for example, surface treatment, that we think makes sense. But the medical device adhesive area has stayed fairly true to what it was under Loctite. We haven't brought a lot of other technology because of the biocompatibility testing. That's the issue. You know, we want to know right up front it's going to pass that before we ever bring it to the line. If it doesn't get a second chance. So I don't know if that completely answers your question, but that's kind of where we are. Any others? Okay, come on. There we go. So, what we're going to start with, and I'll just set this slide up for you. I don't know what the red line down the center is. Is that? This is something that's going on here to distract you just a little bit. But the adhesive joint design section, we stole the slides that you're going to see from our industrial group, because Baxter handles all of the industrial products, the medical products, everything Loctite, right?
Yeah.
He knows it all. I only know medical, a very small portion of that, and I've only been focused on that for about 30 years. So we stole these slides, which were very industrial, very stainless steelish, with the red designating the adhesive. So just bear with me and try to imagine that these are some type of disposable medical device that you manufacture, and eventually we're going to move over into cylindrical parts, which are much more commonly encountered in the medical industry. But if you were to apply some forces to this, if you were doing a design for a medical device, what are some of the forces that you think could act upon our adhesive? Anybody?
Tensile.
What was that? Shear? Any others you can think of?
Feel.
Oh, I think you guys know them all. Oh, come on. I don't. Tensile, compressive, shear, and then we put peel and cleavage together, even though they are slightly different. Which one do you think of those might be the most challenging? Peel? Any reason why, or just is it from first hand experience?
Peel too much or not enough.
Okay, exactly. And when we're working with disposable devices, sometimes we'll say peel and cleavage is extremely challenging for adhesives, but what we find out is you so almost over-engineer the device to begin with that it can really withstand quite a bit of peel forces. What we're really concerned with are the types of things that Baxter runs into, where it's over the life cycle of a component or a material, maybe that's out there for years, it sees a peel force every single day repeatedly. So let's look at the first one and just get some quick definitions out of the way. When we talk about tensile forces, we're talking about two lat shears, one on top of the other, and they're pulling in opposite directions, right? So they have a tendency to elongate or stretch the object or the medical device. Tensile forces are fairly compatible with all adhesives. Most adhesives can withstand them quite nicely. The opposite of that would be a compressive force. Okay, sorry. I'm using a different computer, so I'm using Julian. Oh, okay. Let me just do that. Let's see. I think it's just if I don't move quickly enough, it gets mad at me. Okay, so a compressive force is the opposite of tensile. It's a downward force on your part, right? So it has a tendency to what? Squeeze the object together, just the opposite. And again, compressive forces are quite compatible with all adhesives. I mean, there are very few adhesives that are going to have a challenge with this. The challenge will become to design for just a pure compressive force or a pure tensile force, because unfortunately, one of the other forces typically lags along with it, okay? Shear force looks a little different. You have an overlap and it's sliding motion. I always think of earthquakes because I'm in earthquake country. I'm in southern, you're in northern California. It's that sliding motion over the surface. And actually, shear forces are how we measure the strength of adhesives. We'll put them in an instron, your bonded assembly, and pull in opposite directions and measure the pound pull force on that particular device. Peel, as you can see over the very edge, and cleavage, a little bit different. Any idea what the difference between peel versus cleavage might be? Peel is when you have that flexible surface on the top, and you peel it back, even though I can't do my arm quite that way, like a banana, okay? So you're peeling completely back on the bond line, whereas cleavage is when you have a rigid surface, and you're cleaving or prying at one end, okay? So we kind of have the definitions out of the way. Let's look at another chart that I'll explain to you because you're going to see this repeatedly. At the bottom, you'll see the bonded assembly that refers back to tension and compression, which we combine together because when you go up to the XY chart, you'll see it's expressed as a straight line. In other words, we plotted every stress point on this little XY chart, and it's expressed as a straight line, which tells me it's evenly distributed across the bond line. And that's why tension and compression are good things to design for, and an adhesive can stand them quite nicely. Does that make sense? Let's look at exactly how that works, and I'm going to hope that this little video works. How do you going off? Hang on. What this is going to show you is, again, we stole this from our industrial group, two metal bars placed in an instron, and this is a gasketing material, not really something you'd use in the medical industry. But what it's going to show you is, as you pull in that tension, you're going to see that it's evenly distributed, the stress is, because you're not going to see any particular point on that bonded assembly where the stress is greater or less than, hopefully. There we go. It's a miracle. You see how that's pulling nice and evenly? This is going to actually be what we call cohesive failure, just to give you a sense of what that is. Not something we ever really want to see in a medical device, but sometimes that's desirable if you're doing a gasketing application, again, in the industrial side, with silicones that don't have a lot of integrity or cohesive strength. But you see where there's not really any particular point, it's not cocked or turned any particular way where the stress is greater, right? So let's look at shear forces, and you notice that that looks very different than tensile and compression. We have this interesting U shape, okay? Here's your bonded assembly at the bottom. Again, it's that sliding motion. Where's the majority of the stress being resisted in this assembly? Is it the middle? Is it the end? Not sure? It's the end. Again, if this is your XY chart and you're plotting all the different stress points, the ends are what are giving you the maximum resistance. This center piece is not doing much. It's just kind of sitting there. Okay, so what do I mean by the ends? We're talking about, let me just pretend like this is a bonded assembly. This might show you a little better. So we're pulling in this direction. It's this area. That's what's really giving you the maximum resistance to the overall force that it's seeing. Okay, this center is just sitting there. And it becomes very critical, especially in medical device manufacturing, because you're working with unreinforced plastics that have a lot of bend and give and flexibility to them. And shear forces, as we'll see in a few minutes, can actually turn into peel forces. And we're all a little worried about peel forces, right? So let's just see if that makes sense to you. Now we have a choice. It's kind of a little quick quiz. If we have a choice of increasing the joint overlap here, let me show you what that means. So here's my bonded assembly, two substrates. I can increase the overlap, or on the other side, I can increase the width, this length, this leading edge. And let's assume the bond area is the same, 1 square inch. The force we're going to apply is a shear force. Which of the two do you think would give you higher bond strength and resist more? I see 1 point in there and 1 point in here. Who thinks this is it? Take a chance. Okay, and who thinks this one's one? You're the winner. You win the grand prize, which is a car parked out front, right? I wish. We used to be able to do that. No, you haven't changed the geometry of the end. So let's back up and take a look at this slide. Remember, the leading edges are what are giving you that support. So what you might think is, let's just say you get 1,000 PSI bonding stainless steel to stainless steel. I know when I first started with the company, you might think, well, if I double the overlap, then I'll get double the bond strength. It just doesn't work that way, because you haven't changed the geometry of these leading edges or ends. It's much better if you can go this direction. Because imagine, now you've got these flexing and twisting and pulling on them. You've got a lot more leading edge for resistance. We'll show that in a video that will make a lot more sense to you, because that's a hard one. Again, it's not taught in school, but it's definitely something you want to remember. So, just looking at that a little closer, again, in the still shot, what you're seeing is the bonded assembly, the red's the adhesive. Notice as we start to place that shear force, you see the stretching of the adhesive. It doesn't look like a perfect little rectangle anymore. And in this scenario, you can see now the substrate starting to stretch. And as the force is really placed on it, you can see we're actually moving into a peel mode. And what's happened is, because unreinforced plastic, which is used in metal, or used in medical a lot, it's about 100 times more flexible than stainless steel. So it's going to bend and move with the adhesive. And what we would suggest is, when you see that differential shearing, or you're designing for that, to use a more soft or resilient adhesive, something with a little flexibility and give. Whereas if you were bonding rigid materials, you probably want to use more rigid adhesive. Make sense? Okay, I think this video will show you even better exactly what I was describing, and I think this will leave a good imprint in your brain. What you're going to see are 3 pieces of polycarbonate. The top 2 are put together with nuts and bolts, really widely used in the medical industry, right? No, but that's the business that we're in Loctite. And the bottom 2 are bonded with a more flexible, light-curing acrylic. And we placed it in Instrad, and we're going to start to pull on it, and watch how the plastic starts to bend and flex, and then you tell me which one manages the load better. Let's see if we can make it work. Let's try this one.
This demonstration is a bolt-free demonstration of plastic. We have 3 pieces of polycarbonate. On the top is done with 2 bolts, 8-inch bolts, 25 foot per inch. On the bottom, the 2 pieces of polycarbonate are done with PVC for 30 millimeters. As the load is done assembly, what you'll see is that on the bottom, the pieces stretch out evenly, not less flexible. On the top, the bolts are going to concentrate the pressure, there's radial flexion and further polycarbonate.
Did you hear that enough to kind of get the picture? So what did you see? Did you see the plastic really bending and flexing at both ends as it was being pulled? And it was a pure shear force that we were placing on it. But because they were unreinforced plastic, they were moving quite a bit. So you notice what happened with the nuts and bolts. Where was all the stress concentrated in that area, do you think?
At the contact points.
At the contact points, where you drilled the holes. You put a lot of stress in there just by doing that. And whereas this adhesive distributed the load quite nicely. Okay, let's look at cleavage versus peel. Which one is more challenging based on the slide? Slightly more challenging. Peel? Yeah, it's like peeling a banana. You're really pulling the adhesive back on itself. And I have a little demo that I'll pass around. I didn't make enough for everybody, but even if you do it one time and put the tape back, your partner or whoever's next to you should be able to see how this works. So what you're going to have, take one for me to show you. This is pressure-sensitive tape, and what I want you to do is just first try it in shear, okay, which is a sliding motion. You can do it this way or you can do it this way. And it's strong, no issues, right? Now, peel it back on itself. And feel just a little bit of resistance, and then it just unzips, right? Does everybody feel that? And I'll give mine back to someone that didn't get to try it, so you can see how that works. Easy with pressure-sensitive tape to carry these around rather than bond up a whole bunch of assemblies in my spare time. But what you're seeing is, when you first peel or cleave the part, you'll feel a little resistance, but all the stress is right at that leading edge. And then it just propagates to the bond line, which is what makes it so challenging for adhesive. It just unzips the adhesive. Now, that said, I know of many, many applications where we're bonding balloons on catheters, and one of the tests they do is to inflate it upwards of 50 times, and that's putting an extreme peel force on the balloon. And they give it 110 psi, and it actually withstands that quite nicely, and the substrate fails before the adhesive does. So again, it's starting with a nice, strong bond, good substrates that are good to bond to, and really designing right for the adhesive in the first place. You can do it. Now we're going to switch gears for a minute and kind of move to more cylindrical parts, things that you're more commonly encountering in the medical industry, and kind of apply what we've learned about bonding flat things to more cylindrical parts. Don't see many of these in the U.S. anymore. A lot of this has moved offshore, but imagine a large pressure vessel, kind of a canister, if you will. It could be a blood oxygenator, a heat exchanger, a filter device. And you cut all the way around the perimeter of that device. In the good old days, when I first started with the company, those were bonded with solvent, so solvent welding when it was allowed here in the States. Then customers wanted to move to an adhesive because they found that the solvents don't fill gaps. When their parts came in and were slightly out of alignment or slightly out of tolerance, the solvent just wouldn't fill the gap. And you can imagine if this is holding your blood during an open heart surgery and the thing bursts, because these often see upwards of 400 psi, it would be very catastrophic. So what kind of forces do you think might be acting on that as it's pressurized in use, trying to pull apart? Any ideas? You guys are quiet. No ideas? What kind of forces? It's trying to pull apart, and all the way around here is where our adhesive would be, right?
It's peel.
You could almost argue almost all of them. Peel, cleavage, tensile. And these are often made, I should have mentioned, of polycarbonate or acrylic thin film plastic that you want to move. So what we'd propose is, this is not a good, robust design. We'd want you to redesign that. And one that we would propose is a tongue and groove joint. Anybody here ever worked with a tongue and groove joint? We don't see them as much as we'd like to, but they're just wonderful for adhesives, especially if you're working with light string acrylics, because you have this groove that runs around the perimeter of the device again, and now the tongue comes down, engages, and plows up the adhesive on either side, and that way your adhesive is not as critical as to how much you have to put into the joint, number one, and number two, more important, it maximizes your tensile and your shear while it adheres the peel and the cleavage. You see how that works? So it's a great design if you ever get a chance to design for that. And a close-up of a particular design on a filter device, an arterial filter, is on the right-hand side, just so you can get a sense of what that looks like. So, let's just assume this is a cylindrical part. It could be a stainless steel cannula to some type of hub material, maybe polypropylene, or maybe it's PVC tubing bonded to a fitting of some type, PVC, polycarbonate. If we were to put that in an instron and pull and measure the bond strength, what kind of force would be acting upon it as we put it in the instron and pull? Shear? Good, exactly. Let's assume, and we haven't talked about this, but we'll just kind of test your knowledge, that we're bonding polypropylene to stainless steel. It's a needle bonding application. I already know right up front that I'm going to have a challenge bonding to the polypropylene because it's low surface energy material, right? What are some things you think we might try in trying to maximize our adhesive? We don't get what we want. What is it? Okay. Texture. Roughen the surface? So maybe you could grit blast your stainless steel in this area. What about roughening the inner diameter of the hub? It may help. Maybe not with polypropylene. Not much help with polypropylene. What else? I mean, you have, the choice is yours. It's whatever you want to do to it. It's your design. Primers. Primers can help. They can definitely help with our cyanoacrylate, right? What about plasma or corona, right? That raises the surface energy, which we'll look at. Or what about adding a chamfer right up here and increasing that surface area, right? Anytime you increase the surface area, a lot of times you'll maximize, or you'll see your adhesion go up. Another thing that we've seen in needle bonding, if you're not familiar with it, is to put annular rings or bumps around that inside diameter of the hub material. And that gives you more of a mechanical bond. It doesn't really increase your adhesion, it just gives it more of a resistance to pull for the plug. So, just to review those design guidelines, we want to maximize tensile and compressive. And I put shear up there, even though that can be challenging, but it's better than peel and cleavage, right? And that's what we want to minimize, peel and cleavage, or at least be aware of the consequences of peel and cleavage. And the one that I think everybody learned about is to increase the bond width, or the length of the bond line, over the overlap. The overlap really just doesn't give you much bang for the buck, okay? There's a couple more concepts that we'll talk about. If you ever call Baxter and I because you've been manufacturing for years and all of a sudden parts start falling apart, we really hate it when that phone call comes, but it does happen from time to time. And, of course, you're going to point the finger at us and say, what did you do to your adhesives? And we're going to probably say to ourselves, not to, what did you do to your process? What happened? What changed? So we're going to have to go through some troubleshooting exercises, and I actually included some in the back of your binder so that if you ever get in this position before you call us, it might be just kind of a checklist to go back through your process and be sure nothing has changed. Because a lot of times things do change that you're unaware of. You know, if you think you have it locked down, but an operator decides, oh, you know, I think I'm going to let the light cure product sit out, you know, in the open air for a few minutes because I need to go to the restroom or take a break. You know, these are just the kinds of things that can cause a disaster. So in this first case, does anybody know what the failure mode would be called there?
Cohesive.
Exactly. And what that means is, and you saw that with the metal-to-metal adhesive on either part, in gasketing that I showed you way back in the beginning, the adhesive failed. It doesn't have enough cohesive strength or enough integrity to really give you that kind of bond. I've had that one time in 30 years with the company. So in the medical world, we don't see that very often. In industrial, you may see that because, again, sometimes you want that in a gasketing application. The second one is going to be a problem. If you see all of a sudden the adhesive is sticking to one substrate, but it's not sticking to the other, that's going to lead us down a path of investigation that's very different than either of the other scenarios, right? What are some of the things you might consider if all of a sudden this happened and you'd had excellent adhesion to both substrates in the past?
Contamination.
Contamination. That's the first place I'm going to go. What happened? Mold release, plasticizer migration, silicone oil being used somewhere else in the plant that's moved over onto my part. Or maybe somebody forgot to clean the parts the way they're supposed to be cleaned, right? As is, sometimes when you receive parts is not necessarily the best way. We always like to see an isopropyl alcohol wipe, if you can still use that in your plant, because starting with clean parts generally gives you a much better starting point and a lot more consistency over your operation. This last one is called substrate failure. It's where the adhesive is actually stronger than the substrate it's bonding to. And that's what most customers try to achieve or want to achieve. It's a good thing when we hear that. So you're really not going to call us and complain about that if you see that happen, right? Let's just explore surface wetting just a little further, because that's one of those kind of areas that we don't talk about very often. And what you're seeing on the left is a real tight close-up of a surface. And it's not necessarily metal, but that's the adhesive, the blue, okay? And it's just sitting on the top of those peaks, right? And on the right side, what you're seeing is the adhesive has actually gotten down into the nooks and crannies or the peaks and the valleys. That's what we want to see. That's good surface wetting. These people told us they had to leave early, so we were expecting it. Thank you. There's a whole science behind surface wetting. And if you've ever washed your car, gotten it waxed, you'll notice that it always rains, especially up here probably, and that bead of water sits like a nice, beautiful drop. It just doesn't wet out. It's the same thing with your materials that you're bonding to. If you have a poor contact angle, what we're trying to achieve is all the way over to the right, where it spreads out. You want the surface tension of the adhesive to be lower than that of the substrate you're bonding to, okay? That's what you're trying to achieve. This is not good wetting, this is not good wetting, this is not good wetting. And sometimes that's an interesting test to perform if all of a sudden you see parts are failing, and you wonder, is there something on my surface that's causing a problem? You can just take a drop of water, or the adhesive for that matter. It depends on the viscosity of it, but water works quite nicely. And if it wets out, then you probably got a real good chance of bonding. But if it speeds up like you see here, that's going to be an issue. So just going a little further on surface wetting and how to achieve it, I mentioned to you always starting with clean, contaminant-free parts. I've seen things like just dust give a great amount of variability. Mold release, plasticizers, and PVC can cause some issues. Some of the ways to get around it is to plasma treat, to bombard the part with oxygen, and that increases the surface energy. You can also use corona electrical discharge, which roughens the surface, and again, it's giving you more surface area to bond into. Primers work with dianoacrylates, and of course, good old-fashioned solvent cleaning. So just another sense of the surface energy and what some of the substrates, ranging from difficult to more difficult to bond to, but there's just kind of a mix of all. You can see the initial surface energy that's measured in dynes per centimeter, right? And what happens after we expose it to plasma treatment. And note that the surface energy of most adhesives is 30 to 40 dynes, right? So you want something that's considerably higher. In order for it to have good bonding capability, we'd like to see it at about 70. However, that said, we bond polycarbonate every day, and it's lower than 70 for sure. That's an easy one for us. Does anybody use plasma treatment or corona discharge? You have? It's effective, right? Do you use it just on the low surface energy materials, or?
No, it's all over.
All over.
The trouble is it's time dependent. That's the problem.
Yes, it is. Yes, it works as a good cleaner as well as raising the surface energy. And some people use it just for cleaning the surface. So, let's see. that was it on joint design. Any questions on that before we move to the next segment? No? Okay, we'll go to bonding plastics. Just going to review a couple of things that we ran into when I first started with the company, and one was bonding to plasticized PVC. That since the day I started with our company in 1981, I think, I was told that PVC will be going away in the medical industry. They're going to replace it. It's going to happen. It's going to be gone. And part of it was because of the plasticizer and disposal of PVC in the U.S. We really don't like to get rid of it. It takes incinerators, scrubbers, very expensive. But there has never been a perfect or direct one-off replacement that I've seen. Anything else out there is extremely, quite a bit more expensive. You have to treat it in order to bond to it. So I don't know what's going to happen with PVC, but what we ran into a lot was the DEHP, or the plasticizers, the things that make it nice and flexible, were the things that gave us trouble because they have a way of migrating up into the bond line. And so one of the things we would tell customers back in those days and still today is if you're bonding to flexible PVC and you're getting some real inconsistency or variability in your bond strength, go back, bond some parts, age it, 60 degrees C, 14 days in the oven, and that's going to accelerate any migration of plasticizer in it. And what you may find out is you've got an overwhelming amount of plasticizer that's going to be an issue, that nothing's really going to bond to it. On the other hand, you may find that you can back off that a little bit. You don't need quite that much flexibility, and the product of choice is still 3341. It actually has an additive in it that allows it to overcome the plasticizer. It's an excellent product.
As a what? I'm sorry?
An additive.
Oh, additive.
Yep. I can't tell you what. They don't tell me. Stress cracking. Does anybody ever have this show up in their plant? And I'll pass around two parts, and I hope Baxter will collect them. You're going to see a piece of polycarbonate bonded just to a piece of metal, just to pass it around a little bit easier, but it's stress cracking. I hope you've never seen this in your plant on any part. It's excessive. It looks a little bit like what you see down here. Does anybody know what really causes stress cracking? If you haven't read my slide yet.
Stress relief.
What causes it?
What causes
What causes stress cracking?
Environmental.
Environmental is actually
Solvents.
liquid adhesive or solvent. Solvents can attach the surface of an already slightly stressed part. And what it does is it just opens up and propagates down into those cracking phrases, whatever you see. It can take minutes, it can take hours, depending on the material that you're trying to, put the adhesive on. The more glass-looking plastic, the more glass-like plastics, the more amorphous are the ones that are more prone to it. The ones the medical industry loves to use. Polycarbonate, polystyrene, all of those glass-type materials. The more internal stress you have in the part, like this little fitting that you see right here, this certainly could be one that would have an issue with stress cracking. There are ways to get around that and to avoid it. And so first you want to start with an adhesive designed to minimize cracking potential. And the way we do that, we'll look in the bonding guide in a few minutes and I'll show you how you can look that up. But if you're working with a light curing acrylic adhesive, for example, the one thing you have to do is make sure that you get it to the cure station as soon as you dispense it, as quickly as possible. It's not the time to dispense your parts and go take a lunch break and then come back and cure it. You need to take care of the curing immediately because most adhesives can withstand a few minutes on the part before they'll start to do that. We measure it. I'll show you in a second. But if you leave it for 15 minutes, 20, 30, now you could be creating problems. And if you're working with a cyanoacrylate, you may have to use an accelerator to speed up the cure, force it to cure. Also, you can minimize the internal stresses in the part sometimes, and one of the best ways I've found to really minimize it is annealing. If you really can't make any design changes, you can bring that little fitting back in and you can expose it to a low temperature heat for a specified period of time, and that relieves a lot of the internal stress. Another thing is you could look at the mold design. This would require change. And just be sure that you don't have any really sharp gates in the design. And the last option is to go back and say, all right, I think I'll just use reinforced plastic. Don't see that happen very often. But I don't get a lot of calls these days for stress cracking. Most people manage that pretty nicely. The way we test for the stress cracking potential of plastics is to use this little gizmo on the right that looks like a vise, very small, but we actually place a lap shear in that area, and if you look closely, you'll see the number 2,000, right? So we place the lap shear in it, we put a drop of whatever the adhesive is that we're wanting to test, and we induce anywhere from 500 to 2,400 psi, okay, at that bend point. And then we monitor it over time and measure, you know, how long it takes for that stress crack to show up. So now I want to introduce you to the design guide, and this first one should be under section 2. You might want to pull it out. It might be easier to work with because we're going to kind of go through it. I'm going to show you how to use it because I think it's going to be one of your best friends if you're in the design business. So we just updated this just recently. I think we're in volume 6, okay? So this was a 2-year project for an engineer that used to work in Rocky Hill, Connecticut, now transferred to Ireland, but I remember well when he was working on this data. And I just want to walk you through it because once you learn how to use this one, you'll know how to use the companion rubber thermoplastic guide. There's a third one for metal, but it's not really designed for the medical industry. It's really designed for more structural bonding, okay? So what happened was, many years ago, we fielded phone calls in our corporate office from a customer asking, what's the best product that I can use to bond, I don't know, PBT to PBAT? And whoever answered the phone would say, I'll have to get back to you. There was no repository where we had all of that data in one place. We had lots of customer reports, but we can't share those. They're confidential. So we really needed to develop some really definitive data that gave customers a starting point of what chemistry should I even start with? Which ones can I eliminate? Or is there something I can do to the substrate to make it more bondable? So we looked at a wide variety of plastics that are widely used, and then we actually had some specially compounded for us that we might have added an anti-static agent or glass reinforced, whatever it was that we felt might make an impact on the overall bond strength. And this is what we ended up with, and that's what I want to review with you. It's just kind of how to use it. We'll walk through it, and then if you put this away for 3 weeks or several months, you can always go back to page 3 to 5 and review how to use the chart. Because what looks complicated on first blush really isn't. Let's just start with page 1, table of contents. And let's just, somebody throw out a plastic that you might use to bond.
Polypropylene.
Polypropylene, aren't you nice? Okay, polypropylene. So we should be able to find that one, right? Do you see it on there? Okay, page 62. So, we go to page 62. Everybody find that? And on the left side, you'll always find the generic data for the polypropylene, okay? Just general information about polypropylene. On the right side, and I'll come back to this in a minute, is where we developed shear strength with a variety of chemistries, with a variety of additives to the polypropylene, okay? What if you wanted to bond Delrin, another favorite? You're not going to find that in the front under the description of adhesive, or I'm sorry, not description of adhesive, plastic properties section. You're going to find it in the trade name at the back. So you'd go to page 91, and there you see Delrin, and it's an acetyl by E.I. DuPont on page 72. So it's kind of got you covered, whether you know the generic name or the trade name. And the chances are good that the plastic that you selected is in here. I have found very few instances where I haven't been able to reference what I was looking for medical devices. So let's just look at a couple of other areas before we come back and really look at how to use it. If you go to page 74, okay, you'll see stress cracking potential, stress cracking resistance of various plastics. And what we did was look at our 2 leading categories for medical, cyanoacrylate and acrylic, which in this case are light pure acrylic. And we looked at a lot of different plastics. And I think if you looked at this carefully, you'd notice that it's the glass-like plastic that will have the black circle on it that says you should test it. Could be an issue. You may have an issue. It's prone to stress cracking depending on the molded in stress. So this is just to give you a hint at, am I going to have an issue here? Should I be aware of it if I use one of these 2 chemistries? And a good starting point. Page 75, directly across from it, kind of an interesting guide. You'll find definitions for plasma treatment, corona discharge, and some others that I have never run into in the marketplace, such as iodine treatment. Maybe you've heard of that. And on the next page, there's some more sodium treatment, which is commonly used in Teflon-based materials. And you'll find the description of what that method is, and it'll actually tell you the types of materials that it's used for. So it just gives you some options of, okay, if I work with fluoropolymers, for example, I'm probably going to have to do something to them to get the adhesion where I want it. Another thing that you can look at is page 80, okay? Processor rules for good adhesive assembly. And this is just one to read in your spare time. This was written by one of our engineers a number of years ago, and it talks to the coefficient of thermal expansion and how that's really critical to look at that if you are bonding for a design that's going to see some contraction and expansion. And if you have vastly different materials, you need something to absorb the stresses that it's going to see, maybe a more elastic material. Great article. Page 77. If you want to just review the joint design that we talked about and even go just a little bit deeper, there you go. We'll give you the names of it: scarf joint, toggle joint. I mean, they have names for all of these. The test methodology I've been asked about a couple of times of how did we prepare the samples. That's all back in the back on page 84. Shows you exactly how we prepared the samples that you're going to learn about with shear. And then they added this recently. Did you know? I don't know why they did this, but it's just some kind of interesting little options like shore hardness, mathematical conversions for those of us that are weak in math, and how we measure viscosity and shelf life. Okay? So there are some good things in there that you can always go through, and a glossary of terms. But let's go now to page 41. And I picked a very commonly used medical material, which happens to be polycarbonate. And again, always on the left side, you'll find some generic information about just polycarbonate in general, right? You'll see who the major manufacturers are, what they call it, the price, where it's used, all that good stuff. But what you're probably the most interested in is what's on the right side. And this will be the adhesive shear strength. And again, we're always updating this because we're always making new adhesives, new products. You kind of have to filter through this to find the medical device adhesives, but they're there. So going across the top in this charcoal area, okay, those are the substrates and what we've done to them. So in that first square where it says unfilled resin, that means we took polycarbonate and bonded it to itself and measured the shear strength. And the specific polycarbonate that we use is located right here. Does everybody see that? And in this case, it happens to be Cleavage 300-4 by Dow Chemical. All right? Then, in the next little box, you'll see we roughened the two pieces of polycarbonate, bonded them together to see if roughening had a statistical effect upon our bond strength. Did it? Did it increase or decrease the bond strength with the black mass? It increased it. It went from 750 psi to 1600 psi. And that's why it has that kind of a grayish box. If you go down to the bottom and look, that means there was a statistical significant increase in bond strength. If it had been that kind of the pinkish color box, that means it was a decrease in bond strength. Everybody see that? It's way down here in the notes at the bottom. So as you keep going across, this isn't, adding all of these different things to it. They're one-offs, if you will. So first we measured unfilled resin bonded to itself. Then we did roughened to itself. Then we added an antioxidant. Why do you think we added these things to the base polymer, the polycarbonate? We did it because it might be a fraction of a cent, and it might have a huge result for you. In other words, if you just added this particular antioxidant, that might give you a much higher bond strength. Not necessarily on this material, but you'll find it on some of the other materials. It did have a dramatic effect. Or a flame retardant, something that really didn't cost you much more to add into the formulation. So, Black Max just doesn't happen to be a medical product, but if you look down right beneath it, you'll see 401 and in italics 4011. 4011 is a medical product. What's the bond strength of 4011 and the unfilled resin bonded to itself? Anybody? Oh, come on.
Say again.
What's the polycarbonate bonded to itself?
26.6.
For the product 401, 4011, either one. It could be that second white box, right? 3850. Does everybody see that? Okay. Is there anything I can do to increase the bond strength using the same adhesive? Yeah, it looks like there's a couple of things I could do, right? I could roughen the polycarbonate. Yeah. Or I could add that flame retardant that we referenced. That might do it. 3850 is a pretty nice bond strength. That's not too much of an issue. So if you just go down here, you get a sense of some of the adhesives that we tested. When you get down to this section where you say, well, why didn't they test all of these in the same way? These were recently added new products, and it would have been another 2-year project. So we just wanted to get a sense of, on the unfilled resin, what it looked like, okay? That's the reason you'll see it that way. Now, the other thing comes up is that the best product? If I picked 4011, is that the product that I should use? No, that's just telling you that that particular product is one that's the highest selling in our medical line. There may be 3 other different viscosities in that family that would give you equal results. But that just is kind of pointing you in a direction to go. Now, the other question I'm asked is, well, we never bond polycarbonate to polycarbonate. We bond polycarbonate to something else. So the way you make that work is, let's just say you're bonding it to liquid crystal polymer, page 33. And I hope you're not, because that's a nasty one. So you're going to extrapolate between the two. And what you do is you look at your polycarbonate and say, okay, what are my options? Well, it looks like 4011 is a good option. Looks like I could use 3311. Looks like I could use 4307. I've got 3 different chemistries I could use. Now I go over to the liquid crystal polymer, and I'm a little bit more limited. Looks like 4011, not quite what I'd like them to be, right? 300 psi, shear strength. That's nowhere near the 3850. But the highest bond strength I might see there is 3311, and then look right below it, 4307. So my bond strength is going to be on the low end. In other words, the weakest link is where my bond strength will be. It's going to be closer to that 650, 450 psi. It's going to adhere like gangbusters to the polycarbonate. Not as good on the liquid crystal polymer, right? But it's a great starting point so that you can really make decisions about substrate well in advance. And you can use this guide the same. So if you're bonding something out of this guide to, maybe you're bonding to Kraton or PBAC, widely used, you can look at here and see exactly what kind of bond strength that you might be able to start with. Does that make sense to everyone? Great guide. We use it almost every day. I pull that guide out. Every day, because I can't memorize everything. So it's a great reference tool. Any questions on that? How am I doing on time? Oh, I'm there. Okay, so we'll go on to sterilization resistance and then right into biocompatibility testing. For sterilization resistance, the top 3 are the areas where most medical devices fall. I think most of you are probably contracting out your sterilization. Most don't do it in-house. Gamma radiation is basically bombarding the parts in a 60 cobalt field with the radiation. Often we see 25 to 50 kilograys. We've run some tests I'll show you in a slide coming up. I think it's 100 kilogray cumulative. Gamma radiation is a great way to sterilize parts, but it does typically have an effect on those more glass-like plastics because it's a longer dose or exposure. 6 to 12 hours is not unusual. And so it has a tendency to kind of color change the materials. Makes them more yellow or brown, and that's why you see a lot of polycarbonate out there that's kind of that purplish gray color, so that the shift isn't quite so yellow. We don't like yellow in the medical industry. It makes it look old. It also can embrittle the substrate. And again, because our adhesives cure into a plastic, you just need to think of them as they're a film of plastic, and they can work the same way as my plastics that I'm bonding to. Ethylene oxide is taking that toxic gas and putting your device into a chamber. You pre-moisturize the part so that the gas will actually penetrate harder. Expose it to the gas, then it's removed and de-aerated for up to 24 hours. So I don't know of anybody that's doing that on site. Most adhesives withstand ethylene oxide. We run our adhesives through a couple to 3 cycles of it. An electron beam is the 3rd category. Again, that's a very expensive way of sterilizing parts, so I've only seen a couple of electron beam sterilizers from plant, but it's a far friendlier method than gamma radiation. It's a much shorter exposure. So you don't see that color shift, you don't see the embrittleness as often. These other 2 areas we've listed, but that was when we were kind of going down a path of, let's just see how our adhesives will do with a glutaraldehyde exposure, autoclaving, because sometimes, the doctor or the nurse might open up a package, compromise the material, and then have to re-sterilize it at the facility. And these are often the way they do it. We just kind of wanted to get a feel for how would our adhesives do in that area. So this is a slide. It doesn't really identify the adhesive, but I could go back and find that for you. It was done for a white paper. And what you notice is we used a variety of cyanoacrylates, acrylics, and we measured resistance of different substrates, or initial strength, I should say, retained, all the way up to 100 kilograys cumulative, right? So So nothing there that really gives me any kind of pause. ETO or EO, 1-2 cycles. The one that really kind of concerns me is this one. What do you think might be happening there? It looks like it lost some of its overall bond strength and dropped to 85 or 70%, which might be fine in your application. That may be more than enough bond strength. Moisture could be.
Temperature.
But if you go back and look, it's a light pure acrylic, and we're bonding with a rigid, that refers to the type of adhesive we use, versus a flexible, in this case, but different substrate. I suspect it's that coefficient of thermal expansion. If you look at glass and polycarbonate, they're like completely different animals, right? So I think that's probably what happened, and had we been bonding PVC and polycarbonate, it might have been much higher. So you really need to kind of watch that. You obviously have to do your due diligence. We don't sterilize parts. We don't sterilize our materials before we send them for biocompatibility, but you certainly have to do a sterilization study on anything that you make. We did this about...
So when you do your biocompatibility, those are not sterilized products? Okay.
No, we don't. We're not GMP, and that's, I think, required by GMP. And we're not regulated by the FDA either, so that gets us off a little easier. You guys have to do all the hard work. We just couldn't do it in every configuration, as you can imagine, that a customer might come up with, or every substrate that's available. Now, this is looking at the bulk adhesive. In other words, taking a sheet or a dog bone off the cured adhesive, no substrate, and then running it through a battery of autoclave, gamma, ETO, and then a control group. And what they did was select one that has a glass transition of 82C, which is fairly high, versus one that was 54C, and so on. And then they looked at our UV silicones as well. The control is always just kind of a hot pink color, and you can see this is really the only one that really had some interesting phenomena, and it's because it has the higher glass transition. It actually got stronger after exposure to autoclave, which is very unusual. Autoclave is by far the most challenging type of sterilization method. And luckily, you don't use it that often. But I get a call about once a month from someone who wants to run it through, 500 cycles of autoclave. And that's just not what these adhesives were designed for. And that was looking at tensile, tensile strength at break. This looks at elongation, and it's a little different story, right? But you can see there's really no drop-off anywhere that would really cause you concern. No real loss of properties of the adhesive, right? And so next we'll go to biocompatibility testing. Henkel, back in the early 1980s, and we were Loctite back then, did USP Class 6 testing, United States Pharmacopoeia, and that just included a small battery of tests. Somewhere along the way, and I think it was about the early 1990s, we moved to an ISO test, an international standard, and that gave us more of a global presence. It also meant that we did a much more extensive toxicity test on our products, and we really still have the most extensive testing, I think, in the marketplace of any I've seen. We actually retest our adhesives every 5 years, and we do that just to check and balance to be sure everything's still the way we say it is. So it's inclusive of USP Class 6, and then we do these 3 extra tests. That's the certificate of compliance that you can pull right off the website. They're fairly easy to access, so if you need that for your regulatory people or anybody else, it's there. And I think this just shows you how you access it. If you're lucky enough to get to our website and find it, you can go there and pull off technical data sheets, materials, safety data sheets, the ISO testing, any number of things. Questions? Nope. Okay, we're in the last leg, epoxies and urethanes, which really doesn't fit with the rest of this. This is just a hint of what we're really going to talk about the next time, which will be the adhesives that we sell a tremendous amount more of than epoxies and urethanes. I think all of us think of these as, well, we go there only when we have to, or when you have to, we should say, right? We're going to start with a light pure acrylic or a cyanoacrylic because they're faster, they're convenient, they're widely used. But a lot of times you're forced into this position because you're working with opaque substrates, or you need some better chemical or thermal resistance, or you need a great deal of flexibility. Just to show you our packaging, we acquired Hytol a number of years ago. It's not that we're proud of our packages, but it's just to show you that this is the way we package the products. I'll just pass this around so you get a sense of how it works. It's a side-by-side package. So we've really taken that that bit of mixing with beakers and guessing and all that out of the equation. You just have to know that there's a mixed nozzle that goes on the end, and after you determine that you have completely mixed product coming out the end, then you're good to go. And those nozzles are disposable. You're just going to have to throw them away fairly regularly. We've categorized epoxies and urethanes together, but they're really two completely different types of chemistries. But we did this just in showing you how they cure. Because with epoxies, there's a part A and a part B, a resin and a hardener. With a polyurethane, it's a polyol and an isocyanate. And what we're showing you is this is a 1-to-1 ratio. The two come together when they're combined and mixed out that static nozzle. They combine and start to cross-link and form a cross-linked thermostat material when cured. And even if you're working with our single-component epoxies, they still have two components in them. They just have a latent hardener. And that latent hardener just means that when it's exposed to that threshold of heat, whatever the temperature is for the product, it solubilizes and combines with the resin to start the reaction. You just don't see it as two components. So we always like to look at the evaluation criteria, what they offer versus, other chemistries. Again, most customers pick epoxies because of their chemical and thermal capabilities. They need to go there because they have a higher temperature that they need to achieve, or sometimes they're gaps, cure-proof depth. You could fill this whole room with epoxy. It might be on fire because of the exothermic reaction, but they will fill very large gaps. Considerations. It's always kind of the processing side. That's the part that you have to contend with, that nozzle, that mixing, making sure you don't have off-ratio material, and then taking care to make sure the product hot life is still enough so that you can use it. The clock starts ticking the minute it comes out. You can have a 5-minute work life, you can have a 120-minute work life until it doubles in viscosity, and at that point, that's when we say, it's really not usable. And this is what we have to offer, anywhere from 20 to 120 minutes, a range of properties. They're all in our medical selector guide.
So you have the high salt patch kits now? Or is that still out of there?
No, I think that's in the industrial line.
Okay.
Is it that little
two-part? Well, it's the two syringes. I mean, the two.
Like a little mixed 5-pack, I think it's called.
Well. No, it was actually called patch kit. It was like a 5-minute epoxy. It was wonderful.
I don't know if we still have that. I mean, it's in the
like
industrial.
In a box. It was a yellow box and all that. It was a high salt product.
It may be there. I don't know. It'd be in the industrial line. It's not in the medical line.
Okay.
So that's epoxies other than the single component ones. And we developed these products to address a need in the marketplace. There were several single component epoxies, but we had a specific customer come to us and say, we need a lower temperature to cure the product. The one that they were working with required a 250 to 300 degree cure cycle, and that melted their plastic parts. So we developed a product that could take a lower temperature to cure it. It extended the shelf life. They were also having to receive it frozen and store it that way, and the viscosity changed dramatically if it, defrosted. So we developed these products, and they're available now in the medical line. And then just the fastening on the polyurethanes, there's just a couple of products in our offering. Again, it's a polyol and an isocyanate. We're just showing an application where they're bonding a polyurethane fitting to tubing. They're using our M11FL. The reason that you would use a polyurethane generally is because they're very tough and they're very flexible. They are the only ones that really rival like our silicones, for example, as far as flexibility goes. So catheters, sometimes you're working with catheters that are very opaque surfaces. There's nothing else that will give you that flexibility. We're working on a cyanoacrylate that's close to that, but right now this is probably the only thing that you can go with, and they're two components still. Processing, same concerns and issues that you have with epoxies, but one that we added to it, which is that sensitivity to moisture. You have to be very careful. We send those in a foil overpack to minimize any moisture exposure, because moisture will start to do strange things to it. It'll get bubbles in it. It'll create a very unattractive bond line if you're not careful. So they're kind of sensitive to work with. A couple of products, and I think that's it. And I just wanted to remind you that we have another seminar coming up on May 16th. There it is. Same time, same place, right? Bring your binders, and I think I included both presentations in there. So if you don't make it for that second one, you'll still have the presentation notes. Can you pull over the light? Everybody wakes up. Wake up quickly. lot. Questions?
So for the plastic, do you have also some of those plastics which are not listed here but comparison? Like you have this plastic, it is very much similar to this one.
No, I don't really have a crossover for the types of plastics. However, if you called me and you just said, look, I'm trying to bond a PVAX and I'm getting nowhere with it, I might be able to recommend something from what I've seen in the marketplace without giving away any trade secrets. Like it might be a polyurethane and a Shore A, as options. But often they're very specific to materials that you use, and there aren't crossovers, as you probably know. Raw materials are kind of drying up. It's an interesting time, I guess, for all of us. But in the chemical world, it's a very interesting and a challenging time, just like it is for the medical device manufacturers. Any others?
Yes. Well, I was wondering when you were talking about all this, I was wondering about storage. A lot of these, and you mentioned like polyurethane putting very high percent, very temperature, moisture sensitive.
Right.
And so, is there something that summarizes all of these?
There is, and if you go into your bonding plastic guide, this guide, we've updated the shelf life policy on page 89. It is better, I would say, to look at the TDS of the product because that gets very specific. It tells you exactly what you need. This one's very generic. For cyanoacrylic, it's this. For acrylics, it's this. But at least it gives you that. And on every package, we give you a use-by date. But it is critical to store products properly. I mean, I can't tell you how many places I go into where somebody will think that they're supposed to store a light-pure acrylic under refrigeration, and that's not recommended by us. Room temperature. Whereas the cyanoacrylic, we recommend that you store it in a refrigerator until you're ready to use it. Once it comes out onto your floor, it doesn't go back into the refrigerator, because now you run the risk of introducing moisture back into the product, and that is the trigger that makes it pure. So there are some tricks to storing the chemicals, but we are happy to work with you and educate you on that if you have any questions on specific products. Did that sort of answer it? It's a short answer.
One more?
Yes.
I'd like to dissolve the adhesive without removing the substrate.
Good luck. Okay. Well, what adhesive and what are the substrates?
I would look at, let's say, a polycarbonate as a substrate, and you name the adhesive.
Okay. Since you're going to learn about this a little bit in the next one, but that question doesn't always come up. It's a fine line, a balance, where you want an adhesive that's really strong that will give you substrate failure, and then, oops, I really didn't want that one. And now you want to take it back apart and get rid of it. With the light cure acrylics, polyurethanes, epoxies, and silicones, they all cure as a thermoset material. So when they cure, you can take a blowtorch to them, and good luck with it. You're just going to char them, but it's really not going to make them go back into a liquid so that you can pull the parts apart. So that's a real challenge with those. With silicones, generally though, the bond strength is fairly weak, so you could actually take a razor blade if you were so inclined and be able to peel that off to a certain extent. The others, epoxies, urethanes, no, probably not. Cyanoacrylate's a little different animal. They cure into a thermoplastic, so you can put heat to them. I would recommend a mask or something because the fumes are going to be horrendous as you heat this up. Now it's going to turn into a goopy liquid super bonder, so you need to have some kind of gloves or something. It's just not worth it. I don't care if your part costs $2,000. You really don't want to do that. I mean, it's just hard. You could place it in acetone, but you mentioned polycarbonate. I don't think it's going to do well with acetone. So if you're bonding metal to metal, you can soak in acetone and possibly get it apart, or if it was just a drop or a little bit, you might be able to manage that. But after it's cured, it's pretty much there. So it probably wasn't the answer you wanted, but it's the truth. Any others? We really thank you for your attention, your time, coming here, spending the time with us. We love to give our customers any extra help that we can because we know it's a challenge to navigate through websites and data. That's why we give you everything that we've got in our heads. It's kind of a brain dump for us. But we know that you don't have the luxury of time to read through and know it the way we do. So you can always call us. We're happy to help. Yes?
I do have one more question.
Sure.
So I was wondering about cleaning agents. Is there anything like, there's some clients that are interested in using like enzymatic-based ones. I don't know if there's any high-end ones.
The one that we, unfortunately, solvents and things like that are now so, especially in California, there's hardly any used beyond water, but IPA seems to be the most consistent thing for us, so I don't really have a recommendation on that, but if you find one, the only thing I can tell you is if you batch treat your parts, that can be an issue because now you're cross-contaminating everything. We'd much prefer to see a one-off, wipe the surface so that you're not putting it on each and every part if you do have an issue. And I've seen, there's some tricks to that too. I've seen customers that are bonding with our cyanoacrylate do a phenomenal job of cleaning. Okay, so they clean the parts, now they're going to dry them for 20 minutes, and they're going to immediately bond them, and our adhesives don't work. And the reason is they've driven off all the moisture, which is the trigger that makes cyanoacrylates work. So, you can go almost too far. We need some surface moisture on there. You need to let it reacclimate to the relative humidity in the room if you're working with cyanoacrylates. It's not usually a problem with the other adhesives. But I don't have a recommendation to you, Baxter, on a specific cleaners that kind of varies. I mean, the plastics and the substrates that you use can't take a lot of things.
We have that solid figure too, like I was the
yeah. Stress cracking is one of the things you can run into, yeah.
And actually I'm thinking about another client, they had issues with trying to accelerate like a silicone-based material, trying to cause cure, even if they're at like a certain number of hours, they're trying to accelerate that. Really case by case.
It depends on the adhesive too. Like in the medical, we have two pure UV visible curing silicones. That's the only thing that will cure it. Light has to get to the bottom line. We have a third one that has a secondary relative humidity moisture with vulcanizing cure. So you could expose it to relative humidity higher and bump it up a little bit. And sometimes heat, even with our acrylics, you can give it a little bump of heat and that'll get it there faster. Not much you can do with cyanoacrylate. It's just kind of like you have to wait for that 100% stream. And we do recommend that. You don't want to move parts while they're still forming at fixture time. Yep.
How do you define this expiration date on these adhesives?
On the adhesives? Well, on the bottle, there will be a use-by date on there.
No, I mean, what makes it expire?
What makes it expire? Well, we have an internal and an external date, which I know sounds confusing. It even confuses me some of the time. But what that means is we have taken into account there's going to be transit time from, let's just say we're manufacturing this particular product in Puerto Rico, which is where a lot of the medical products are made, to Louisville, which is where we store the products, and now maybe it's going to sit there for, 2 weeks or a month before our distributor, RHU, says, oh, we have an order for that, let's pull some in. So now it gets on a truck and it moves out to, where are you, Oakland or San Leandro now? Yeah. Right, San Leandro, okay, and it sits there until they send it to you. So we have to take into account that it's going to see some fluctuating environments, to take these temperatures until it reaches its destination and it's stored properly. So that would be the internal shelf life. The external shelf life is what you're going to see, is how much time from the time that it sits at the distributor's shelf do you have left that you can use it. And generally speaking, you're going to have a minimum of 6 months shelf life. I mean, if you have less than that, you need to let the distributor know that that's not acceptable. You only can use something that has 8 months shelf life. But the maximum on most of our products is a year shelf life from date of.
Well, we are running with that issue.
We
are not getting that 6 months shelf life.
Okay. Do you know what product it is?
You get maybe 3 months shelf life.
Ooh.
My question is that, after 3 months, we know that adhesive is not just expired.
Mm-hmm.
It's not totally unusable. But when you want to use it, do you have any kind of a standard procedure?
It depends on the adhesive. If we're a cyanoacrylate, I would say the day that it stops, get rid of it. Because when they go bad very quickly, and it's you can usually see it, but the strength will drop off and everything will go south very quickly because they're very sensitive to moisture and being refrigerated. Acrylics, I've seen them last well over a year. I've seen them last 2 years. But you're a medical device manufacturer. Do you want to risk that? So I think you have to do some internal testing to justify it. You could also call us, and we can see if we can do a recertification sometimes. It just depends on the product. Do you know which one it is that you've gotten 3 months on?
I don't have the number right now in my mind.
Does it seem like it's a cyanoacrylate?
We are issues again and again. We are throwing away more adhesives because it expires.
Before you can use it all? If you can get a handle on your forecast and, maybe do a buy spec, that's another thing I haven't mentioned, but a buy spec is an excellent way to manage that. And it's a buy specification where you write down, I want your product to meet XYZ, maybe a viscosity, tack-free time, some things that are right off the TDS, and then you might also put a clause, and we would like for product to have a minimum of 9 months use by date, shelf life. I think 9 months is about the most you can expect, because you have to allow for some transit and sitting on a distributor shelf. Because we move a lot of products across the United States, but RSUs is really one of our best distributors. They are actually our best distributor for medical products. So the chances are good that they have fresh material, but I'm sure they're doing first in, first out, and unless you talk to them about that, they may not even be aware that that's what's happening with you.
Is the product you guys get pretty regular?
Pretty regular.
Yeah, I mean, working with Mark and internally there, I saw the emails going through. If it's just set up kind of this is what we want, and then from their end, they kind of want to know the forecast, and then if they know the forecast throughout the year, they can just work with you.
They said that you need to buy a whole box, whole case.
Oh, okay, so it may be broken cases, and you may be, okay, maybe not a widely used product. It almost sounds like it's not one that they're selling to a lot of other customers. If you can get back to back, so we can work on it. Definitely work on it. Any others?
I got a question kind of for the group. So is there kind of like a takeaway? Because I know Kyle always does these seminars, and I'm always kind of interested to see what kind of takeaways you guys have. Was there anything you guys didn't know before you got here, or applications that you guys think that this knowledge can help you with?
The book's good.
The book? The bonding guys? Yeah, the bonding guys.
Any projects that you're working on that you're challenged on right now? Because we're going to be here for a few minutes cleaning up, so you're welcome to hang around and bring those to us.
I need a cup of coffee. I'll be back.
Make sure that you sign this.
Oh, thank you. Yes, could you sign the sign-in sheet to prove that we were here? Thank you.
Let's do a good for a round.
Oh.
Round of applause.